Okay, so now let's do an example of drawing equivalent resonance forms. Okay, so let's draw the complete Lewis structure, which may include more than one structure, for sulfur trioxide. Go ahead and pause this presentation and try to draw the Lewis structure for this molecule with sulfur as the central atom. Okay, so step one, basically we're going to connect the atoms together with sulfur as the central atom. Okay? The next thing we're going to do is we're going to count the valence electrons. We have one sulfur, which contributes 6 electrons, and 3 oxygens, which contribute 6 each, for a total of 24 valence electrons. Now remember, you could have done this before you connected everything together. Either order of these two steps is just fine. All right, so then we're going to count the electrons used in the connectivity, okay? So 1, 2, 3 bonds, 2 electrons each, 2, 4, 6 electrons were used in the connectivity. All right, so then we're going to distribute the rest of the electrons, and we're going to complete the octets on the outer atoms first. Okay, so remember we've used 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we're done with that step. What do we do next? All right, so now we need to check to make sure every atom has an octet. So going back up to this picture, does every atom have an octet? What about this guy? See, sulfur does not have an octet. So now we're going to have to move a pair of electrons. So let's go ahead and take this pair and put them into a double bond. All right, so you can see down here, now sulfur has an octet, and there's a double bond with one of the oxygens. Now, when we're talking about equivalent resonance structures, this is the key point. Why did I move this pair of electrons here? Couldn't I have just moved this one instead? Or this one? And the bottom line is that there's no reason why I picked this one versus moving a pair from here or here. Okay? Basically, if all of us sat as a class and each of us picked a bond to make double, we would probably, each of us pick a different one, and we'd have 1/3, 1/3, 1/3, with 1/3 the class picking one way and 1/3 the class picking another. Okay? So bottom line is that's the key feature of equivalent resonance forms. All right, so now let's go ahead, whichever one you drew, go ahead and calculate the formal charges and add them to your Lewis structure. Okay? All right, so oxygen here has a 0 formal charge. All right, 6 valence electrons. After division, this oxygen has 6. Okay. Sulfur has 4. Okay. I should have put a +2 on that sulfur, by the way. All right. 6 valence electrons, so +2 on sulfur. And then on these outer these outer oxygens, the ones without the double bond, then we have 1, 3, 5, 7, 6 valence electrons. So we overall have 1 extra electron. So a negative formal charge on those 2 oxygens. Okay, so what about the other equivalent structures? So go ahead and draw them. So draw all of the 3 possibilities. Okay, so and then be sure to put in the double-headed arrow in between all of these equivalent resonance forms. Okay. So bottom line here is that all 3 of these guys exist at the same time as a superposition, okay? They all exist at the same time. Okay, so we talked previously about calculating partial formal charges. All right, so pick one of your drawings and add up the non-zero formal charges on the outer atoms, okay, on these equivalent atoms that we're looking at. We're going to ignore the sulfur 2+, okay? Basically, we're only adding up formal charges on these oxygens, and then we're going to count the number of equivalent atoms. So there are 3 equivalent atoms and -2 in charges. So we get a partial formal charge of -2/3 on each one, okay? So if we were to just imagine this, we'd have -2/3 here, -2/3 here, -2/3 here. Okay? All right, so what about bond orders? Okay? So again, pick one of the structures, which I have mine right there, and we're going to determine the number of equivalent bonds, which are all of these, okay? This one, and this one, they're all equivalent bonds. And we're going to count up the number of bonding pairs, okay? So 1, 2, 3, 4 bonding pairs, okay? Put that right here, divided by 3 equivalent bonds, or 3 equivalent bonding areas, okay? So when we divide that out, we get a bond order of 4/3. So basically 1 1/3. Makes sense, right? Each one has a single bond, and then this last second bond, or this double bond here, is equally split between the 3 regions to have 1 1/3 bonds for each sulfur-oxygen bond. All right, so the actual structure of sulfur trioxide, as we've said, is an equal blend of all of these, okay? So all these bond lengths are actually the same. They're a little bit shorter than a single bond, okay? But not quite as short as an actual double bond, okay? And again, they all have a partial formal charge. -2/3 partial formal charge on each oxygen atom.